you came in. Today we are starting a very short thermodynamic unit. And so we're changing gears a little bit away from conversions. We're still going to have some math, but now our math is associated with phase changes and amount of energy for these things to happen. So we are going to just start by reviewing the names of the different phase changes. This is something I expect you guys to know. And so I have little figures here for you guys to use. And so the one all the way on the left, this will represent a solid. In the middle, we have our liquid. And all the way on the right, our gas. And so if we first start all the way with our solid, the arrow going between solid and liquid, this would be melting. Taking it one step further, adding energy to that liquid, it now begins to boil. So this is boiling when we go between liquid and gas. Now coming back the opposite direction, starting with a gas and going to liquid, this is called condensing. And then when we go from liquid to solid, freezing. We do have two more phase changes that can happen. They're more rare, but when we go from a solid to a gas, does anyone remember what that's called? Starts with an S. Sublimation. I think I heard it. So sublimation is going from solid to gas. What about going from gas to solid? Deposition. Okay, hold on. I got a couple peeps in here. All right. And then I think I heard the last one, deposition. So again, this is kind of review, but I want to make sure you guys know that you need to know these for the upcoming test. So what I'm going to do is play this video that kind of shows on a molecular level what's happening and how temperature is affecting these phase changes. So if I go
point of this simulation, what we have is a block of ice. And so what you can see with each one of the dots here in the middle of the speaker, those represent assortment of molecules of water that are stuck frozen in that ice cube. We are heating it at a constant rate of heating, and we're going to watch this thermometer as we start this simulation. So what we see here is as this ice is heating up, right? So we had ice starting at a temperature below zero, and as we heated it, the temperature rose on the thermometer. Now watch what happens as the temperature reaches 0 degrees Celsius. We start to see the molecules of the ice cube get loosened up and turning into a liquid. Notice that while the ice is melting, the temperature is staying constant at 0 degrees Celsius. Once the water has been all melted into liquid, the temperature can then start rising. And so the temperature will start rising, the molecules will move faster and faster, the kinetic energy is increasing. And at some point, certain molecules will have enough kinetic energy to actually escape out of the liquid and turn into a gas. And you'll see here, as the temperature approaches 100 degrees, that's when those molecules have enough kinetic energy to escape and float away. Notice while the temperature is remaining 100 degrees Celsius. By the liquid water is being used to accelerate the molecules out of the liquid phase. Once all the molecules are converted to a gas phase, the temperature begins to rise.
I just wanted to give you guys a little bit of a visual representation on phase changes and what happens when we increase the temperature. So we need to think about how temperature is related to kinetic energy. Increasing the temperature increases the energy of those molecules to move even faster and change phases. And so now we're going to give a graph, kind of show what is happening with phase changes using a graph, a visual representation for this. And so we can think about these pictures again, depicting things like our solid phase. If we go to the second figure, this is showing that both solid and liquid are kind of together here. I'm going to use a plus sign instead for now. And then we have our liquid phase. we have what looks to be a liquid and a gas phase are present. And then lastly, just our gas phases. So these are kind of the 5 steps that are happening going from solid to gas with all of those phase changes in between. And so what the graph is showing us is the relative temperature and how long it takes to do so. I think I forgot to make sure this didn't get cropped, but think of the bottom axis as time with units of minutes. And so what's happening here is if I'm going to give each one of these points where the line segments change a letter, let's call this point A where it begins and point B. So what's happening between point A and point B? Well, first off, this is where our solid phase exists and it's starting to warm up. So at this increasing slope of a line, what we're going to have is our heating up our solid. Now, if I add a third dot, point C, and look at line segment BC, this is at a plateau. There is no change in temperature. But what's actually happening right now is that our solid is, I'm going to change colors here. Second, our solid is turning into a liquid at this segment. What is the phase change name from going from solid to liquid? Melting. So as we could assume at this temperature, we call this our melting point or MP. Then once we melt all of our solid into liquid, we move on to segment C. And of course, I'm going to label this next point D. So between point C and D, this is our liquid phase that is now beginning to heat up. Once it hits 100 degrees Celsius, then between D, and I'm going to add our another point E. So this is our second plateau. We actually have our liquid trying to go to the gas phase. So our second plateau is going to be at our boiling point. And then lastly, we are going to increase energy temperature between E and F. And so really here we have all of the gas phase, but we're just heating up the gas even more. So this is what's called a heating curve. So we start off at low temps, go to high temps. We're adding heat, and this is of water. How do you think I know this is water? Okay, pretend it doesn't say that. Exactly, because of the things like boiling point and melting point, which we can identify off these graphs. We know water melts at 0 degrees Celsius. We know it boils at 100. So these are identifiers that allow us to be like, yep, this is the heating curve of water. Now, when we add energy to a system, we have a special term for that. It's called endothermic. So we would call this graph an endothermic process. So the whole entire thing, the whole time we continuously increase our temperature. So I'm going to add that we are increasing temperature. I keep doing that today. Increasing temp. And then I just want to make sure you guys remember what endothermic means. This is when we have energy absorbed by the system. In our case, the system I'm talking about is the water. So in endothermic processes, we are adding energy. So energy is entering the system endothermic. So I'm trying to start right now, you guys, special ways to remember endothermic is adding energy. Any questions on heating curves before we look at the opposite? All right, so the next thing we're going to talk about here is cooling curves. So when looking at cooling curves, we're doing kind of the opposite trend here. We're starting at a high temp and going to a lower temp. So what I want to point out here is the phases. So I'm going to quick and throw down all of these little labels for each point. So A through F, just so I don't have to do them each time. So here are the different points, A, B, C, D, E, F, are 5 little line segments. And so when we're first looking between A and B, what phase do we start in if we start at the highest temperature here? gas, exactly. So we are starting with our gas phase between this segment here. Our first plateau is between B and C, but this is at the higher temperature. So we know we're going between what two phases? Exactly. We are going from gas to liquid. What do we call this? What type of phase change is this? Condensing. So this plateau here at 100 degrees Celsius, we now call that our condensation point. Then as we continue traveling down, we are in our liquid phase here. We are cooling our liquid, cooling until we hit 0 degrees Celsius. Then we have our liquid that's going to start going to solid. We call this our what point? Freezing point. So at 0 degrees Celsius at the second plateau, we now have our freezing point. Once all of the liquid turns to solid, then we have just solid as our last phase here as we continue to cool that down. So now we call this exothermic. How you can identify if the curve is an exothermic curve is that we have temperature decreasing, and instead of energy being added, we have energy or heat is released from system. In our case, again, our system is working with water. So endothermic energy is entering, exothermic energy is exiting. Now, one thing you might notice is if I look at specifically this condensation point. The condensation point of water is at 100 degrees Celsius. We're going from gas to liquid. If you look at the boiling point from the heating curve, going from liquid to gas, that's also at 100 degrees Celsius, which we should expect. Where things go from liquid to gas and gas to liquid should happen at the same temperature. It just depends if we're adding or removing energy. And so one thing I want to point out, I kind of am a little bit ahead of myself, but that's what these dots are for, is that the freeze or the condensation point is going to happen at the same exact temperature as the boiling point. What do you think this means for the freezing and melting? The solid to liquid, liquid to solid points. They're also going to be the same. They're both going to be 0. So at your freezing point, that will be the same temperature as your melting point. So depending on which direction you're going is if you're either adding or removing energy, but they happen at the same temperature. So when we summarize an exothermic versus endothermic heating curves, if I'm just going to keep working with water, we know we have important temperatures at 0 and 100 degrees Celsius. So I'm just going to put those at the exact same spots on both graphs. If I have an exothermic graph, energy is being what? Gained or released? Released. Exothermic energy is exiting, it's being released. If we're releasing energy, we are actually decreasing our temperature of the system. So exothermic, we start up at towards the top. We decrease our energy into the first plateau here, that first plateau being our condensation point. So we're starting from our solid, or sorry, our gas. At our condensation point, we are going from gas to liquid. Once we have everything in liquid, we can start cooling again to our next plateau. So I'm just going to label that this is the liquid portion. Then our liquid can go to solid at our freezing point and then continue on. So this is an example of exothermic, where again, we have that condensation point and that freezing point on the plateaus. thinking about the endothermic portion, now we're gonna pretty much have the mirror image if we're still working with water. Endothermic energy is entering. We are gonna show an increase in temperature, so we start at the lower portion. So we start somewhere below 0, start increasing, hit our melting point. We're gonna keep increasing up to our boiling point, plateau there for a while as we change all of our liquid to gas, increase our temperature and gas. So labeling these phases, we start out with solid. We then have our solid convert to liquid. Liquid heats up. Then we have our liquid go to gas and our gas phase. Except now we have different names for our plateaus because of the direction we're heading. Solid to liquid, melting, liquid to gas, boiling. But notice how these are at the equivalent temperature. So if I ask you for all 4 of those points, you should have 2 pairs that have the same exact value. If I ask you for the melting point and the freezing point, you'll both write 0. All right, any questions before we talk about this kind of using equations? Okay. So for those endothermic phase changes, things like melting and boiling, things that take energy to happen, we are going to break these down. So melting goes between what 2 phases? Solid and liquid. So what we're going to do here is write H2O solid on the left hand of the arrow, because if we're melting, we start with solid, then we go to H2O liquid. So I'm writing an L on the right hand side. Now, you may notice that there is a spot right here to add something else. What do we keep relating to phase changes with? Change in what? Temperature, which is related to energy, right? So we have an energy term that is related to this phase change. So for water to go from solid to liquid, it takes 1,440 calories. Now, calories are a unit of energy. And so you guys have probably heard about them on looking at the back of any food that you have purchased before. And so calorie is just a unit of energy. And it says, if I have 1 gram of this thing, this is how much energy it takes for me to increase the temperature of 1 gram of this 1 degree Celsius. So it has to do with amount of energy to increase the temperature. This 1,440 calories is what we call the heat of fusion. This is specifically the value heat of fusion for water. So heat of fusion is this many calories for water. What is the melting point of water? When does solids start to turn into liquid? You guys should know this, 0 degrees Celsius. Now, if we talk about boiling, we are starting from that liquid phase of water, and we're going to the gas phase here. We have a new energy term called the heat of vaporization. So we could think of vaporization as creating a vapor, creating a gas. So it makes sense that this should be along the liquid gas phase boundary line. The value here is 9,730 calories. Now, even if you don't have the best idea of what a calorie is, you should be able to tell that it takes more energy because the value is higher. It takes more energy to go from liquid to gas than it does solid to liquid. So this new term here, heat of vaporization, belongs with this value. What's the boiling point of water? 100. Now we have the last process, sublimation. This is going from solid to gas. So this is still endothermic. You have to add energy for this to happen. This is a rarer type of phase change. It doesn't happen for everything. It does happen for water, carbon dioxide. If anyone's seen dry ice, it just goes right to the vapor form for iodine. And so there's no fancy term for this energy, but the amount it takes is 11,170 calories. Now, These are the endothermic phase changes. That means we're adding energy. Notice how when we add energy, we put the energy term on the left-hand side of the arrow like it's a reactant. So that's one thing to pay attention to, is if the energy is on the left side of the arrow, we're adding it. So when we talk about exothermic reactions, we're going to use that energy term on the right-hand side as if it's a product. So when that energy is released, it's released as a product. And so first we're going to use freezing as an example to show this. So freezing is now going from liquid to solid. When we do that, we release energy. Guess what? We release that same amount of energy it would have taken to go from solid to liquid, but now we release it as we go liquid to solid. So freezing uses that same heat of fusion value. What's the freezing point of water? 0 degrees Celsius. Condensation, this uses the heat of vaporization. Again, we're going to keep that same value as going from liquid to gas, except put it on the right-hand side. Because as we go from gas to liquid, we're releasing that energy back out into the world. Lastly, what's the condensation point of water? 100 degrees. So notice how condensation and boiling have the same value, freezing and melting have the same value. Then we have deposition. This is going from a gas to a solid. This uses that same value that we saw with sublimation. 11,170 calories. Again, exothermic, right-hand side of the arrow as a product, endo enters left-hand side. All right, for this next portion here, I want you guys to practice drawing a cooling curve. So pay attention, you're gonna have to figure out what direction it goes. A cooling curve for water starting at 130 degrees Celsius to -30. I want you to label the temps for condensation and freezing point. Use those hash marks there for the condensation and freezing points. Going through this with you, what you should have done is if we see the word cooling curve, we're going to cool this thing down. We're going to start at a higher temp. And so I'm just going to throw on my important temperatures onto my y-axis real quick. So this is going to go from 130 degrees Celsius to -30 degrees Celsius. And I know my important temperatures for water happen at 100 degrees Celsius and 0 degrees Celsius. Now, cooling curve, I'm going to start at that high temperature, that 130, and I'm going to draw a negatively downward sloped line until I hit my first important temperature of 100. That's where I'll draw my first plateau. I'm going to continue on decreasing to my next temperature of 0, draw my second plateau, and then another decreasing line. So thinking about what phases we have here, we start with our gas phase because we're start at a high temp. We then know our first plateau is going to be going from gas to liquid. This is our condensation point. So I would label this 100 degrees Celsius as my condensation point. Then we are cooling our liquid down even further until we start going from liquid to solid. This is our freezing point. So I would label this 0 degrees Celsius as my freezing point, and then solid at the bottom. So gases live at the top portion of these graphs, solids live at the bottom, liquids go in the middle. Yeah.
Label it as condensation point if you
It'd be endo, but no. You would label that as your boiling point. And so we'll do that for this next one here. So this next one, we're doing a heating curve for nitrogen. And so now we're working with a different substance, which means we're going to have different values for our melting and boiling point. So for nitrogen, its melting point is -210 degrees Celsius. Its boiling point is -196 degrees Celsius. So I wouldn't worry about going up to 60. This graph isn't scaled very well. Maybe go to like -150. Oops, and I can't write that either. Otherwise, this would be a very poorly scaled graph. We are given the melting and boiling point. So your temperature should always go from smallest to largest. But with negative numbers, that means negative 210 goes towards the bottom. Then we have negative 196, because as we are heating up, we're increasing in temp. I'm gonna call this negative 150 up here for now. And then negative 250 down here. So heating curve. If I'm heating something, I start at that low temperature. I plateau at my first important temperature given. Then I continue heating to negative 196, plateau, and then continue on. So I think you guys are probably confident in your basic shape of a heating and cooling curve. Now thinking about phases. Solid phase lives towards the bottom, so we're starting with solid. Our first transition is going to be solid to liquid. This is what? Our melting point or boiling point? Melting point. So we're labeling our melting point happening at negative 210 degrees Celsius. Then we are traveling as a liquid, getting warmer, warmer, warmer until liquid starts turning to gas. This is now our boiling point at negative 196 degrees Celsius. Till finally, we're all in gas phase, continue heating. Any questions about heating curves? Okay, so for those of you that have your computers and computers charged, there is a little activity online. It's just one Google slide having you guys drag these different things to label onto a graph. So I want you guys to do that. And then this worksheet as well. And then I did post a pre-lab, but you guys don't have to worry about that till Thursday. So we have a lab on Thursday. Don't worry about the pre-lab right this second, but work on that little activity. It'll take you probably a few minutes, and then the worksheet. It is on Google Classroom.